Hey guys, BuildZoid here, and today we are going to be taking a look at MSI's RTX 3080 Gaming X Trio PCB. So, the PCB pictures are, of course, from Tech Power Up's review of the card. There will be a link to their review down in the description. I strongly recommend you go read that because it covers all the things that I don't care about very much, like thermals and noise and power. Well, actually I do care about the power limits, but here's the thing. If I told you their results from their review, I'd basically be stealing their work, so that's not cool. um, but yeah, so if you want like more in-depth information about the card that isn't just like components and power delivery stuff, which is what this video is going to cover, I strongly recommend you check out the review of the card from Tech Power Up. There's the link in the description. And so, yeah, thank you to Tech Power Up for, having high-res PCB pictures in their reviews. And with that out of the way, let's get into it. So, Gaming X Trio, this is one of the, it's definitely one of the more custom RTX 3080 PCBs out there. It is still very similar to the reference design, though. And honestly, it's not really very impressive. So, yeah, I'm a bit disappointed with this card. Um, for like the triple 8 pins, check out like the thing about the triple 8 pins, like check out Tech Power Up's review and you'll realize how pointless it is to have that many 8 pins on this card right here. But yeah, anyway, let's talk about the power delivery. So for the for the 30 series, we of course have this really awkward layout of the VRM where it's like I can't go like, oh, this is the V core because it's not in one place. Um, Anyway, so in terms of the actual phase assign, yeah, there we go. That's how that's split up. And then on the other side, we have this lovely mess, which is kind of the norm for a 3080. So we have three main rails here. We have VMem. Actually, that's dumb. You have VCore, you have VMem. Actually, no, that's still the wrong order. Uncore. Like I've decided. So in the previous video, I called it VCore 2. But since then, I've actually found out that it's basically like the secondary core power rail is basically for powering things like caches and memory stuffs. And the closest equivalent that I can think of for like CPUs would be the Uncore rail on Intel chips with a fully integrated voltage regulator. So I like the idea of calling it Uncore because it's part of the it's still like it's not a memory controller rail, right? Which if you called it like memory system, then some people might be like, oh, it's for the GDDR6X memory chips, but it's kind of for that, but it's not just for that. So yeah, I like calling it Uncore because it's things inside the GPU core that aren't the actual core, which, yeah, or inside the GPU die that aren't the actual core. So I like calling it Uncore. And then we have, of course, VMem, um, which is the memory power rail. So those are our three main. And I've screwed that up. We should put it. Man, there's not enough space here. I should have extended the image a bit. So VMem. It's going a little bit over what I assume is the PEX rail, but minor voltage regulators aren't really that important. Like they're important as in if it doesn't work, the card doesn't work, but it doesn't really do anything for overclocking 90% of the time. So you may as well ignore it. Like I don't really care about them too much. So anyways, those are our three main power rails. In terms of the arrangement, we've got one phase of VMem over here. We got another phase of VMem over there, and then one more phase of VMem down here, which is pretty much the norm for RTX 30 series GPUs to have the memory VRM just scattered all around the board. The idea behind this is that it makes the power distribution between all of the memory chips a little bit more even because let's say you put all of your memory power delivery up in this corner, right? Then this memory chip down here needs to get all of its power from all the way over here. And so you have current flowing through the PCB like so. And the problem with that is the power plane that current is flowing through, obviously it's very low resistance, but it's not zero resistance. And so you will get a potentially significant amount of voltage drop going from, the voltage regulator to the actual memory chip. And also just like these memory chips are closer to, the memory VRM. So the problem you run into with that is if the voltage drop going from like this point, like from say here on the board to here, is, say, 50 millivolts, which is a lot, but it could even be like 30 millivolts, it would still potentially be a problem because the GDDR6X memory is specified to run on 1.35 volts. That's the minimum operating voltage that you're supposed to be running these chips with. Now, theoretically, at lower speeds, you might be able to undervolt them, and they do tolerate some amount of overvoltage, but by spec, you should be running them at 1.35 volts. And so if we wanted to achieve 1.35 volts on this chip over here, and we have 50 millivolts of voltage drop across our power plane, then, you know, these chips over here have to be at 1.4 because we lose 50 millivolts across this distance. And so the workaround to that is, well, what if we don't try to cram all of the power into the memory chips from one point, but instead feed the memory chips from multiple locations on the PCB. Now, MSI has kind of like gone out of their way to negate as much of the benefit of distributing the memory VRM around the PCB by basically putting the memory VRM phases as far away from the memory chips as they could, right? Like, the hell is that? Or this? And I guess also that explains why they decided not to use this memory phase. Because the funny thing is, if you look at the actual NVIDIA Founders Edition, NVIDIA very specifically uses like this phase because logically this phase is the closest to these memory chips. So if you're not going to have 4-phase memory power, you should be using this one, a voltage regulator right here, and a voltage regulator right there. And that's what you would see on a Founders Edition PCB. But MSI basically decided that they're going to move their VRM back, which might have some benefits for reducing the thermal density of the PCB, which might translate into slightly lower operating temperatures. Also, it might just be a case of them reusing their fin stack design, and so they didn't really feel like shifting where the VRM cooling was supposed to go, so they just moved the entire VRM instead. You know, Asus does that on a lot of their GPUs, where it's just like, we have one heatsink design, and if the VRM is not where the VRM is not where the heatsink intends for it to be, we will redesign the PCB for the VRM to be where the heatsink wants it to be. So yeah, that's how you end up with some cards where you just have, you know, big empty spaces like this, where it's just like, well, the VRM heatsink, the cooling system is designed to have the VRM here, and therefore we will put the VRM there, even though it would probably be better if we actually had it, you know, somewhere here from a pure power delivery perspective. But anyway, so because MSI has basically moved all of the memory power delivery far away from the core, having one of the phases significantly closer, like way closer to the memory chips, could actually lead to the same kind of problem that, you know, you would have if you had all of the memory power coming from one corner, because the distance, like the resistance between this phase over here and these memory chips would be significantly lower than the resistance between, say, this phase and these memory chips in this area. So I think that's why they decided not to go with, like, not use this phase. Because the thing is, the voltage controller does not have support for 3 different levels of, like, voltage. It has one input for monitoring voltage levels, and so it's just like, you better make sure that the power distribution through the power plane is relatively even, because that controller isn't able to regulate against multiple different points in the power plane. So yeah, anyway, so we've got 3-phase memory power, which is the norm for RTX 3080s so far. There might be one exception to that, but we'll get to that when we get to that. So 3-phase memory power. Then for the V-Core, we've got these 3 phases over here, and then these 5 phases over here. And I'm not I think the decision not to use that phase was basically a power balancing thing, maybe a thermal density thing, but yeah, I think it's mostly a power balance thing. Like, this might be hooked up to the PCIe slot, and then they were like, yeah, we don't want more power coming from the PCIe slot there. So anyway, yeah, we've got 5 more phases of V-Core over here. So the V-Core VRM is a 8-phase, and then for the Uncore VRM, we've got these 3 phases over here, and then 2 more phases over here. And so that is actually, like, in terms of phase counts, this is completely standard RTX 3080 design right here. It's actually less phases than what you get on the Founders Edition. If you're wondering about the Founders Edition PCB breakdown, that will be up on Gamers Nexus as soon as I manage to make a smaller take, or, well, actually no, I already have one take that I sent off to Gamers Nexus, and they're like, it's a bit too long, Buildzoid. Can you try to make a shorter one? We'll see. They might have to just chop up the 35-minute take I sent off. Anyway, Yeah, so we've got 853. So for most of the most of the like AIB 3080s, this is the standard VRM configuration, something like 853 in terms of the phase counts. Um, and so for controllers, what MSI is using, and this is actually one of the things that I do like about what MSI has done. Like, I'm not necessarily a huge fan of them shifting the power delivery really far away from the chip, but the thing is, there are ways to work around that, so that's not a huge concern. But what I am a fan of is the controllers that they've opted to use, because for both VCore and Uncore, we've got UP9512s. Now, I'm going to assume this one is for VCore just because it's on the upper, like it's above the other one, and the Uncore rail is below the VCore rail in terms of like on the front of the card, right? Like Uncore's down here, VCore's up there. So yeah, anyway, so I'm assuming this is VCore. I might be wrong about that, but it's probably VCore. And the controller here is a UP9512 controller, which is a significant upgrade compared to the UP9511. Now, it's still an 8-phase controller, but it goes all the way up to 2 megahertz switching frequency, and it's somewhat digital, as in it has an SM bus interface. I don't think it has like straight up I2C control, because some controllers will actually give you, like, you can adjust everything. And I think the UP9512 only really allows you to adjust like efficiency stuff, so like phase shedding, output voltage as well. To just at that point, like, you may as well have control over output voltage, switching frequency. But I don't think, like, I think load line is still analog, and so there's some, like, it's not a fully digital controller like some of the other controllers out there where it's just like you can set everything over an I2C interface. Well, with this one, you can't. The UP9512 is supported by the Elmore Labs EVC2 voltage controller, voltage control dongle, I think I should call it. Like, I think it stands for external. Whatever. EVC2. Like, just look it up. Elmore Labs EVC2. You can connect it to various controllers. The UP9512 is one of the supported controllers, and it gives you voltage control and various monitoring functionality as well. Because that is actually supported on this chip. It does support power, I think, current and maybe temperature monitoring. So. Yeah, the UP9512 is nowhere near as dumb as the UP9511, because the UP9511 was completely analog, only went up to 600 kilohertz switching frequency. Still an 8-phase, though. But yeah, the UP9512 is significantly more capable. So that's a nice little upgrade from MSI, especially considering that it's not really like... I don't think any serious overclockers are really going to be... Like, for serious overclocking, I think ultimately everybody's just going to use 3090s, because the 3080 is just not going to stand a chance against a 3090 in 3D Mark rankings. Even if the difference is like 10%, like 10% is the difference between being, top 10. Or actually, depending on how many 3090s get sold, that's the difference between being top 100 and not being top 100, right? So, yeah. It doesn't really... Like, making really fancy 3080s just doesn't really make that much sense. Then for Uncore, we've got another UP9512. So again, you could, control. So basically, the neat thing here is with an EVC2, you can control, the Uncore VCore and the Uncore voltage, because both of the controllers are digital. And this one is obviously just configured for 5 phases instead of 8. Also, you should probably not go all the way up to the 2 megahertz maximum switching frequency, because funnily enough, on a lot of controllers, the max switching frequency setting is actually like not fully functional. It's not properly supported. It's kind of like, well, technically under some conditions, this might work. And if you want to mess with it, you can, but it's just like you shouldn't actually use that. And the other issue is power stages generally don't support. Like, most power stages only support up to like 1.5 megahertz, and even at 1 megahertz, your power efficiency really starts to tank. So it doesn't make sense to go all the way up to 2 megahertz. But up to about a megahertz, it might give you some overclocking capability, like some improvement in overclocking, because you might get slightly better voltage regulation. Anyway, so that's the 2 main power rail controllers. For the memory power, we've got this controller over here, which is an NCP, NCP 81611. And this is a 4-phase controller. This thing is goes up to 1.2 megahertz switching frequency, and it's also very digital. In fact, I think this one is more controllable than the UP9512s, except some idiot didn't put that in my notes, so now I'm not 100% certain about that. But yeah, like the thing is, this one actually has a public data sheet, so you can go look that up. And so that goes up to 4 phases, but here it's obviously running in 3-phase mode, so yeah. Though the option to have that 4th phase did exist. That's why there's 4 memory phase options on the PCB, even if they're not all being used. So that's MSI's controller selection, and honestly, it is a better, selection of controllers than what you get on some of the other 3080s out there. So, I do like that's neat. You get more switching frequency support. You get actual digital controllers. So if you do have an EVC2, you can control them. I guess also if you actually for the NCP 8116. Potentially you could actually control these with Afterburner's I2C interface commands. Though I don't think you can get the UP9512, I don't think it has a public register map, but the NCP 81611 I do believe does. So if you wanted to tweak your memory voltage, you wouldn't necessarily even need something like an EVC2 to do it. You could do it, the hard way on your own. Anyway, so that's the controllers that MSI has opted for in the power stage department. This is not like it's kind of interesting. These are still 50 amp DR MOS parts, but they're slightly worse than say the Alpha and Omega 50 amp DR MOS components. Though at the same time, that might just be a difference in how each manufacturer tests their power stages and then writes out their data sheets, which is kind of annoying. But it's one of those things. So basically, margin of error. Anyway, the power stages that MSI opted for, NCP 3021 50s from On Semiconductor. And these are 50 amp DR MOS components. They do have a thermal flag functionality, so they're dumb, but they're not so dumb that they won't like automatically shut down if they're overheating, or at least tell the controller, "Hey, I'm getting kind of hot. You should maybe do something about this." And also, I suck at including the A there, so yeah. So they have a thermal flag, but they don't include like current monitoring. They don't include any kind of they don't include any of the advanced monitoring functionality that you'd expect from like a smart power stage, or any of the extra safety features that a smart power stage comes with. Being a 50 amp DR MOS component, the efficiency also isn't exactly spectacular, but honestly, for everything that isn't the Founders Edition, currently all the cards that aren't a Founders Edition are on 50 amp DR MOS components, so yeah, that's really not like a huge... Like, I kind of wish MSI had opted for better parts, but at the same time, nobody else is if you want better power stages, it's a Founders Edition, and that's it. Like, that's the options right now, so I guess, yeah, well, like, I'm kind of annoyed, but at the same time, this is going to be fine for stock operation, especially considering the power limits that this card comes with. So, yeah, can't complain about it too much. Like, the choice of power stages here makes sense. It's just, like, it's not as good as the Founders Edition. And, I mean, I guess the card isn't supposed to really... Like, it's actually kind of weird, because basically everybody has a better heatsink than the Founders Edition, because the Founders Edition is like 2 slots, and, Nvidia's actually trying to make a reasonably sized card, whereas everybody else is just kind of like, but big heatsink is better heatsink. And I agree with that. Bigger heatsink is better heatsink. But yeah, so the thing is just... but then on the power delivery side, it's actually the Founders Edition seems to be currently basically the best option there is. So for vCore VRM efficiency, what we're looking at 1 volt output voltage and 500... Oh, that's the other difference. Yeah, so Alpha and Omega semiconductor power stages on the Zotac card, those actually have documentation that includes like performance at 300 kilohertz, whereas the On semiconductor parts only have performance at 500 kilohertz, and then 800 kilohertz and also 1 megahertz, which is just like... yeah, nobody's actually going to be running them at 1 megahertz, so that's not... Man, that's not the greatest 5 I've ever drawn, but it's better than the other 2. Anyway, so 1 volt, 500 kilohertz switching frequency, 200 amps output. This VRM is going to be kicking out about 21 watts of heat, which that's in line with what you'd get on the Zotac card. Doing 240 amps output, it's going to produce about 29 watts of heat, which I believe is still basically in line with the Zotac card. Nope. What did I press? Okay, 280 amps, it's going to be producing about 40 watts of heat, which, yeah, that's not great. But that's actually still, like, I think that's slightly worse than the Zotac card. So basically, at, like, the lower currents, the NCP parts seem to perform almost exactly the same as the alpha and omega semiconductor parts, and then at higher currents, these actually have a slight disadvantage, but it's, like, single-digit wattage disadvantage. It's not, like, a huge difference. So I wouldn't really care about it too much. Also, both, like, the Zotac card and this card both have power limits that should, like, really make the high current draws that I'm talking about here kind of like, yeah, unless you physically modify the card, you're not hitting this anyway. Anyway, 320 amps, the VRM would produce about 52 watts of heat. And this is also where the documentation ends, because like most 50 amp parts, the efficiency curves only go up to 40 amps. Yay! So there. Basically, this is about the same VRM performance that you would get from most of the reference-based RTX 3080s. Like, to be fair, MSI basically took the reference PCB and then stretched it out, and they've made some adjustments that I do like the, digital controllers, though admittedly I think Palette also has a bunch of digital controllers, so that's not really that special. I think Zotac is the only ones who actually have... I think Zotac... I'm not 100% certain on it, but the UP9511 choice by Zotac, I think, was like extra downcosting measures compared to just the regular reference PCB. Anyway, so that's the VCore current handling capacity. For the Encore, we're looking at same 1 volt output voltage, 500 kilohertz switching frequency, but obviously significantly less current because that's just a 5-phase. 100 amps output, you're going to be looking at about 10 watts of heat, which is about the same as the Zotac card. 150 amps output, it's going to be about 18 watts of heat, which is still about the same as the Zotac card. And then at 200 amps output, it produces about 33 watts of heat, at which point I think it's somewhat ever so slightly worse than the Zotac card. So, yeah, basically, like, this is just another flavor. Like, this is a really stretched out reference RTX 3080 PCB is what this is. So, yeah, that's the core and uncore power delivery. And, like, the thing is, ultimately, the VRM temperatures might actually be better depending on how MSI's design their cooling system. But, yeah, like, the actual components here aren't anything particularly spectacular, at least in terms of power stages. The controllers are nice, but the power stages are kind of like, 50 amp DRMOS. We've seen this before. Memory VRM is the exact same situation. And memory power, you're going to be looking at actually, wait, no. Oh no, I'm stupid. Well, my notes are at 1 volt, so we're just gonna roll with 1 volt. I'm very sorry about that. Like, the thing is, it wouldn't really make that much of a difference if I scaled it up to 1.35 volts, but I'm kind of annoyed that, yeah, it's at 1 volt, because it should be at 1.35, but... Anyway, so 30 amps, it'll produce about 3 watts of heat. I think if you scaled it to 1.35 volts, instead of 3 watts, it would be like 3.5 watts, which... Ultimately, I would still round that down to 3 watts. If you're rounding to the nearest watt, I'd be rounding that down. So, actually, well, 3.5 you'd round up, but I'm not sure that it would even make it all the way to 3.5. Because going from 1 volt to 1.35 volts, actually, no, that would put it around 4. Yeah, anyway. So, really, like, it wouldn't make too much of a difference. But this is, like, less accurate than what I'm not normally at. But memory power is not really that intensive most of the time. Anyway, 45 amps output, it's going to produce about 4 watts of heat. If some idiot had done their notes correctly, it would have probably been 5. 60 amps, it's going to be about 6 watts of heat, and 75 amps, about 8 watts of heat. So, yeah, basically the same as any other RTX 3080 available right now. Actually, you should probably add like plus 1 watt to each of those, because again, this is at 1 volt when it's supposed to be at 1.35, because, yeah, like, I've done 2 takes of it, or no, I've done several takes of this video. I'm not redoing it this time. I'm done. I'm not fixing my notes. Anyway, so, yeah, there's the memory power delivery. And then I've already mentioned that's probably the PEX rail, so that powers like the PCIe interface, and we've just got some GS Tech integrated buck converter for that. Then down here we've got another, minor rail. This should be 1.8 volts. I say should be because honestly it would make more sense to me for this to be the PEX rail, but I think it's the TUF that actually labels this as PEX. And the thing is, the BGA of the GPU is going to basically, like, a lot of where the VRM is located relative to the GPU core is dictated by how the BGA is configured. So if the TUF has the PEX rail up here, then the BGA is probably configured to take PEX power somewhere in this area, or like somewhere in this area, and so it doesn't make sense for to have a power plane that goes up here, right? Like that doesn't make sense. So if one card has the PEX up here, then basically all of the cards should have it up here. Anyway, 1.8 volts is supporting rail for the GDDR6X memory chips. Yeah, we've got another one of these GS Tech fully integrated buck converters. You can actually read the part number. I'm not... Like, the thing is, it's a minor rail. The only reason you would really care about this is if you want to vault mod it, and these are relatively easy to, actually, is it GS Tech or ANPEC? I can't remember, but these are actually part numbers that are relatively easy to Google. So, yeah, if you want to, that's GS 9219. So, yeah, that shouldn't be too hard to find if you want to vault mod that rail. Though, generally speaking, the 1.8 volts rail for GDDR memory systems doesn't really do anything. Like, it has to be present for the memory to function, and it's very important that it's present in order for the memory to function, but it's like raising the voltage or lowering the voltage doesn't really tend to do much of anything for overclocking range. So yeah, it's just kind of like that voltage regulator exists, but that's about as much as you need to worry about it. What else is there? Right, so that's the minor rails. I guess we could talk a little bit about the capacitor configuration. Oh, and I talked about the memory VRM power distribution. Well, the vCore is like the vCore VRM being laid out like this, and the Uncore VRM being laid out like this is the same idea as the memory power distribution, just for the core. Because with the amount of current that GPUs pull, you can actually get a significant voltage drop just going from like one edge of the GPU to the other edge of the GPU. So it makes sense to, feed current into the core from both sides instead of from just one side if you want more even voltage distribution to the GPU core. So that's that. And for the capacitor configuration, this is actually one of the other things I do like about this card. So, like power stages wise, this isn't a great, like the card isn't very impressive. The power connectors are completely unnecessary, but I do appreciate that MSI has decided to use a hell of a lot of SMD capacitors, at least on this side of the VRM. So this could translate into a slight advantage in terms of voltage regulation compared to some of the other RTX 3080 sort of non-Founders Edition PCBs, because a lot of the non-Founders Edition cards are or at least I can't wait for when I actually do the reference PCB, because that PCB is really cool from like a cost-cutting perspective. Like, it's really interesting to look at how many different variations of components that PCB supports. But yeah, MSI here, they've actually decided to use the more expensive, lower ESL, lower ESR, SMD. I'm assuming those are aluminum polymers. They look a hell of a lot like Panasonic aluminum polymer capacitors, so I'm going to assume they are. But yeah, SMD capacitors are just great for their ESR and their ESL, which translates to better voltage regulation, which could lead to slightly better overclocking. Though then on the other side of the VRM, we have the standard, low-cost through-hole aluminum polymer capacitors, though MSI is at least using a 5,000-hour variant of those. So that's nice. And then on the back of the card, what's actually kind of significant is there is differences in terms of the bypass capacitors directly behind the GPU core. So MSI has opted to use just more of these 470 microfarad caps, which I appreciate because I've actually seen some 3080s that have like 220s right behind the core. And that could lead to, a slight, again, very slight voltage regulation advantages in favor of this card, which could translate into a couple megahertz. And when I say a couple megahertz, I mean somewhere in the range between 5 and maybe 20 megahertz more core clock at the same voltage, assuming exactly the same quality silicon, just because these do have the higher capacitance just gives you a slight voltage regulation advantage right behind the core. So yeah, I appreciate MSI's choice of capacitors. And then also they have all of these tantalum polymers for the input filtering. But the thing is, I'm pretty sure the reason why these are all SMD caps is not because MSI actually cares about the superior ESL or ESR that they offer. Though the ESR, you can actually get like 5 milliohm ESR on these and 5 milliohm on those. So that's not really the biggest difference. Though you can get 3 milliohm ESR SMD capacitors, except they're like SMD caps are normally pretty expensive relative to their through-hole counterparts, and then when you look at like the 3 milliohm variants, they're like extremely expensive compared to their through-hole counterparts. So I don't think I've not heard of a card using the 3 milliohm variants, but actually AMD might have, because they had like the 3-terminal SMD polymers from Panasonic, and those are like the ultra low, like ultra high performance package for that Panasonic offers. But yeah, these are just 2 terminals, right? You don't have the middle tab that you get on the high performance variant. Anyway, but I don't think MSI is really using them here to get an edge in overclocking, though they could give them that, a very slight edge. I think the main reason why these are being used over here is to just make space for more fin stack. Because that's the thing, is just like they like they're the biggest benefit these have if you're designing a heatsink is just like, well, they don't stick straight up out of the board. They're really low profile. They're barely any taller than the memory chip. So if you're building a big fin stack, these make more space for fins, therefore a bigger heatsink. But they can also lead to a slight voltage regulation advantage. So that, I think it's cool that MSI decided to use those, even though I don't necessarily think that they're using them because they're better electrically. Anyway, other than that, MSI has also added a bunch of input protection, like a bunch of fuses on the inputs, which so the fuses are kind of interesting. Like the thing they do prevent is, let's say one of the power stages does explode. What the fuses do is they'll, after the power stage blows up, because generally speaking, the power stage dies much, much faster than the fuse can blow. But once the power stage dies, the fuse should blow. And the good thing about that is when the fuse blows up, it prevents the sort of like, because the thing is, if you power cycle a VRM where a power stage is shorting the input to the output, every time you power cycle it, you are causing more and more damage. Now, if you have these input fuses, assuming a power stage blows up and then the input fuse blows, every time you power cycle it, you don't actually cause more damage because the fuse has blown and you're not applying 12 volts to a shorted out power stage anymore because it's disconnected through the blown fuse. So these are like, these don't prevent the card from dying. It just makes repair potentially much easier than if you didn't have the fuses and the power stage just explodes, and then your only protection is how quickly can the power supply realize that there's a problem. Because some power supplies respond relatively slowly to short circuits. And so the fuses just add as a sort of like damage mitigation system rather than a damage, like they don't prevent the damage, they just minimize it. So is that mitigation? I think I'm misusing the word, but it doesn't really matter. Anyway, so that's what. So the fuses are kind of a nice addition, I guess. They certainly should help MSI with RMAs, if anything. Now then, for the power monitoring, we have, of course, the insane array of just shunt resistors freaking everywhere. So we've got, what is that? 5 big shunts over there, then 1 more over here. So this one's for the PCIe slot. So actually the cool benefit with the fuse right here is I'm pretty sure if you desolder the fuse, that disconnects the PCIe slot. So you could like desolder this and then just bridge that to one of the 8 pins. And if you were shunt modding, like power modding the card, you don't have to be worried about overloading the PCIe slot anymore because you can disconnect the PCIe slot by disconnecting the fuse and then reconnecting that power input to one of the 8 pins. Though you might want to like it could get kind of complicated doing that, but you could also just add your own, like a 4th 6-pin power connector for that. That would also be an option. So I kind of like the fuses from a modding perspective as well, but for like if you don't like using a soldering iron, the fuses really don't do much for you. Is kind of what I was trying to get at with them. Anyway, so yeah, we've got what is that? So that's 6 big shunts on the front, then there's a little one over here, and I think the rest of them are on the back. So what I've noticed is I think all of the 3080s come with, yeah, so we've got one over there. one over here, and there should be one more. Because I'm pretty sure all of these cards have 9 shunts total. That's not a shunt, that's a bridge. That's like, you'll notice it has 0, 0 on it. So, like, that's a bridge. That's not a shunt. There should be a third one somewhere. Or am I misremembering this? 1, 2, and on the front we've got 3, 4, 5, 6, 7, 8, 9. What? Wait, there's 7. Oh, yeah. Yeah, so there's 9. So, like most 3080s, this has 9 shunt resistors, which is just completely ridiculous. And all of those shunt resistors are being monitored by this chip, and I believe there's a second one of them on the back. And yeah, this chip right here, and that is a US 56, well, both of them are US 5650s from UPI Semiconductor. Unfortunately, there's no public data sheet for these, but from what I have read about them, it seems that basically all these do is they convert the voltage levels on the shunt resistors down to voltage levels that you can feed directly to the GPU core. So in theory, you wouldn't necessarily need to mod the shunts if you just kind of fake the functionality of the 5650, which might make for a cleaner card than modding all of the shunt resistors. But I'm not sure. Like, I'd have to have a card in hand to look into that. But anyway, so that's the current monitoring chip on this card. And I think that's it at this point. Like, I think I've said everything I have to say about this card. Yeah. So basically, the Gaming X Trio, again, I strongly recommend you read Tech Power Up's review because it covers things like the power limit on this card, which explains why the 3 8-pins on this card are just completely unnecessary. Oh, I forgot to mention. Oh, wait. Nah, that doesn't matter. We're not going to worry about it. So, yeah, the 3 8-pins on this card are unfortunately completely unnecessary. Read Tech Power Up's review to find out why. Link in the description. But in terms of other things, like in terms of power stage selection, this is about the same as any other reference-based RTX 3080. In terms of capacitor selection, this is actually one of the better cards because we have the SMD capacitors over there. And then in terms of voltage controller selection, this is also better. Like, this is not the worst card in terms of the voltage controller selection because we do have the UP9512s as well as the NCP81611. So we have, you know, better voltage controllers, better capacitor configuration, roughly the same power stages, and yeah, so like this, like the thing is, I still, like with the 3 8-pins, I was really hoping for something more impressive in terms of the PCB, but it's not the worst PCB out there. It's definitely not the worst. It's also just like, it's not very impressive. So yeah, that's kind of it. So there, that's it for the video. Thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I've got a Patreon. There's a link to that down in the description below. There's also the AHOC Teespring store where you can pick up shirts, stickers, posters, you know, the usual YouTuber merch. Both the Patreon and the Teespring store help out with running the channel immensely. So if you check the links out, that would be great. And yeah, that's it for the video. Thank you for watching, and goodbye.